repeat any questions that are in the audience.
Okay, we're good to go?
Good to go.
Okay. Hi, everyone. My name is Gabriela Silva. I'm a third-year PhD student in the Department of Biostatistics at Brown. My dissertation work here has been focused on improving methods used to profile providers. And in my time at Brown, I've also been working on analyzing data from the VA. So specifically, I've been looking at 30-day mortality rates and how our conclusions regarding 30-day mortality rates vary depending on the set of risk adjustment variables that we use. So today, we are actually going to be talking about cohort studies and case control studies. So let's get started. So today what I'm going to do is I'm going to talk for both of these, for both cohort studies and case control studies. I'm going to describe features of each. I'm going to discuss very briefly some of the statistical analyses that you might want to conduct after having conducted a cohort or a case control study. And I'm going to describe some potential sources of bias when it comes to these study designs. And then finally, for each of these, I'm going to describe two different case studies. For cohort studies, we're going to be talking specifically about the British doctors cohort and the nurses health cohort. And then for case control studies, we're going to be focusing on the inter-heart study and the bulimia study. So a cohort is defined as a group of people with a common characteristic or experience. This word actually comes from the military, and it was used to describe a group of 300 to 600 soldiers. But it helps capture what exactly a cohort study is doing. In a cohort study, what we're doing is that we're grouping people based on their exposure status. So you have some sort of group of individuals that you want to study, and this group of individuals hasn't yet developed the outcome. That's actually a very important part. They are at risk for developing the outcome, but they haven't developed it yet. And then we classify them based on whether or not they're exposed, so on their exposure status. That's why in this image, you see one group that's been exposed and another group that's unexposed. And then what the basic premise behind a cohort study is that we're going to be following these individuals over time, and we're going to be seeing who develops the disease in both the exposed group and in the unexposed group. So that's going to involve the outcome assessment. So what you end up with within a cohort study is a group of individuals that are classified based on their exposure status, as I mentioned. So there's a group that's exposed and a group that's not exposed. And then within each one of these groups, since we're assuming here that the outcome is a binary, you either have the disease or you don't, or you have the outcome or you don't have the outcome, within each of these groups, either the outcome develops or the outcome does not develop. So this leads to 4 potential subclassifications for every single individual in your original study population. There's a group that's been exposed and in which the disease develops. There's a group that's exposed in which the disease does not develop. And then there's a group that was never exposed in which the disease develops, and a group that was not exposed in which the disease also does not develop. So in a cohort study, if you believe that your exposure is positively associated with the disease or the outcome, meaning that being exposed leads to a greater rate of the disease or outcome, then you'd expect these boxes to look in this way relative to the previous slide. We'd expect that individuals who were exposed very, very frequently develop the disease, while individuals who were not exposed tend to not develop the disease. So that's why we see these differences in the sizes of the boxes. One thing that I think is a very good question at this point is, okay, what's the difference between this cohort study and an experimental study, which is one of the study designs that we actually talked about in a previous lecture. In an experimental study, what happens is that you have a population and you randomly allocate individuals to their exposure status. So you say, okay, this person's going to be exposed, this person's not going to be exposed, and so forth. The investigator is kind of deciding who is exposed and who is not exposed. And this should be a random process. The difference between this procedure and an observational study like a cohort study is that in an observational study like a cohort study, the individuals the investigator doesn't get to decide who's exposed and who's not exposed. The individuals actually self-select their exposure status. So what I mean by this is that in an observational cohort study where the exposure is something like whether or not the individual smokes, this is a decision that the individual makes. The investigator cannot themselves say, oh, we're going to say that a group of individuals is going to be exposed to smoking while another group is not. And so just by kind of thinking about this motivating example with smoking, we understand why in some situations, even though a randomized experimental study might be considered the gold standard, it's not always feasible or ethical, because you can't, with a lot of issues that we're interested in investigating, you can't randomly allocate individuals to be exposed or not exposed. You kind of have to understand that some individuals are going to be exposed and others are not, and you can't manipulate that because it's just not ethical to expose individuals to something that may be already known to be harmful. So kind of really understanding this distinction, while in an observational study, the exposures are going to be self-selected, in an experimental study, the investigator decides who's exposed and who's not exposed. The reason why I think sometimes people might want to confuse these two is because in both a cohort observational study and an experimental randomized trial, the direction is from the exposure towards the outcome. But yeah, the way in which individuals were originally exposed is the distinction here. This distinction actually has really, really big effects on the way in which you conduct your data analysis. So for an observational study, like our cohort studies, since individuals selected who was going to be exposed and who wasn't going to be exposed, we need to use multivariable methods in order to adjust for this, while in experimental studies like randomized control trials, you can just use the data as is. The reason why the data analysis is impacted is because when individuals are self-selecting whether they're exposed or whether they're not exposed, it's very, very likely that there's reasons behind those choices. And so it's necessary to adjust for those differences upon wanting to calculate some association of interest. So going back to our motivating example, the individuals who in a randomized control trial, the individuals who end up being exposed versus not exposed, on average, they should be about the same because this was a random allocation. However, in the observational study, the individuals who were exposed are likely going to be very different than the individuals who were not exposed. So the individuals who chose to, for example, smoke are likely going to have different baseline characteristics than the individuals who decided not to smoke. So that's why in our data analysis, when we're trying to estimate different association measures of interest, we need to adjust for this. So I would definitely say that an experimental study design, if it's conducted properly, is going to have a simpler data analysis, but the experimental study is going to have a simpler data analysis, but then observational studies, it's going to require a little bit more work because of this key distinction where exposures are self-selected. So this leads us to cohort studies, which, as I've been alluding to, are a type of observational study. Cohort studies are the most common. They're more common than randomized control trials, and it's by necessity. What I mean by this is that even though, as I mentioned, randomized control trials are the gold standard because they do allow us to infer causality, we can't always conduct them due to ethical and financial considerations. And so a lot of the times we are left with the information provided by a cohort study. In a cohort study, since individuals are self-selecting their exposure status, we're basically observing nature without intervening and taking advantage of people's natural exposures. One thing that's interesting is that a cohort study, what it's trying to do in its data analysis is actually to replicate a randomized control trial or an experimental study. So as I mentioned, in an experimental study, the group who was exposed is going to be very similar to the group who was not exposed when it comes to the baseline characteristics. But that might not be true in a cohort study. So what the statistical analyses are trying to do in a cohort study is to make it so that these two groups are as similar as possible. And so that's why the analyses methods for this type of study design really matter and can end up being a little bit more complicated than for experimental studies. So when exactly should you conduct a cohort study? You have some ideas and some associations that you may be interested in considering between an exposure and an outcome. The situations where a cohort study are going to be desirable is when you don't know much about the exposure, because when you don't know much about the exposure, you're going to want to learn more about it through the cohort study. And the cohort study, since you're following individuals with the exposure, is going to allow you to gather more information about it. Additionally, cohort studies are going to be desirable to conduct when you expect some sort of large effect to come from this cohort study. So when you expect that the association between the exposure and the outcome is rather large. What I mean by this is that if, for example, the exposure leads to the outcome very, very rarely, then you might not want to conduct a cohort study because it's very likely that most of the people that were exposed won't actually end up having the outcome or disease. So yeah, we're going to want to conduct a cohort study when many of the people who were exposed are actually going to develop the disease, because that's going to allow us to learn more about it. Additionally, a cohort study works really, really nicely when we're trying to look at how one exposure can affect multiple outcomes, because since you're selecting individuals based on their exposure status, this is going to allow you to follow them for multiple outcomes. And I've kind of alluded to when it might not be desirable. Cohort studies don't work well when the disease or outcome is rare because they're inefficient, since many of the people who are exposed won't actually end up developing the disease. And they also don't work well when the potential for loss to follow-up is significant, because what ends up happening is that many of your study population might end up dropping out, and that's going to end up impacting your results. Yes. That's a good question. Oh, sorry. When you're looking for a moderate to large effect, how large is what you need? I mean, I think you'd have to do some calculations. Like, so for example, if you know that the disease or outcome only has, I don't know, 1% chance of developing, and you have 10 people who were exposed, you'd have to kind of be like, okay, the chances of anyone in that exposed group actually developing the disease are like really small. So maybe we need more people to be exposed, or yeah, maybe the study design isn't going to work so well. In a situation like that, and we'll talk about the study design, you might want like a case control study instead. But yeah, I think that's an important consideration prior to starting this. And that's why we kind of grouped cohort studies and case control studies together, because if the disease or outcome is rare, you might be better off doing a case control study. But yeah, that's a great question. So as I mentioned in the beginning slides, with a cohort study, we end up with 4 potential categorizations. There's individuals who were exposed and developed the disease, which we're going to denote as individuals in category A. There's individuals who were exposed but did not develop the disease, which are individuals in category B. There's individuals who were not exposed but developed the disease, and those are the people in category C. And then finally, we have category D, which are the individuals that were not exposed and did not develop the disease. So if we go back to think about the association between the exposure and the outcome, if it were in fact a positive association between these two, we'd likely expect this A and D values to be quite large. So most of the exposed people have the disease, and most of the not exposed people do not have the disease. But that's a little bit hand wavy, so we're gonna actually discuss some measures of association that help us quantify that information a little bit better in future slides. But yeah, this is actually a 2x2 table, and it's very, very commonly used in epidemiology to summarize the results of a cohort study, a case control study, I think also a randomized control trial. And they can be helpful because they allow you to capture this information. This is just a 2x2 table, so it's rather simple, but you can have multiple different levels to this 2x2 table, which would make it n by 2 or whatever table, depending on the number of levels. So the reason why epidemiologists like this 2x2 table so much is because you can actually gather a lot of information from it. With cohort studies, based on the setup that we have with these 4 potential categorizations, we're able to calculate lots of numbers of interest, and more importantly, many proportions of interest as well. So we have these 4 proportions: the proportion of exposed with the disease, which would be A, because that's the number that is exposed and has the disease, divided by the total number exposed, so A plus B. We also have the proportion exposed without the disease, the proportion unexposed with the disease, and the proportion unexposed without the disease. And by being able to infer these proportions from this 2x2 table, this is going to allow us to be able to make certain statements regarding the strength of the association between the exposure and the outcome. So before we get into those measures of association, I did want to briefly talk about some of the time issues that come into play with cohort studies. There are 3 different categorizations of this time issue for cohort studies. Most of the time when we think of cohort studies, and the ones that I've been talking about, they tend to be prospective cohort studies where you first categorize individuals based on their exposure status, and then you're following them over time to see who develops the outcome and who does not. And these are very, very valuable because they allow us to infer some things about temporality, and they allow us to really follow our participants through time. However, a lot of the times prospective cohort studies can take a really, really long time to actually complete, and they can be very, very expensive and require a lot of resources. So many times we also rely on the information from retrospective cohort studies. So in a retrospective cohort study, what ends up happening is that we group participants based on their exposure, but by the time that the study has initiated, we already know who develops the outcome and who doesn't. So I'm going to actually show an image that I think will help clarify the distinction between the two. But they're both types of cohort studies. For some study designs and in some study questions, we might actually instead be interested in an ambidirectional cohort study, which basically combines some elements of prospective and retrospective cohort studies, and it allows us to study both short-term and long-term outcomes. So I think these images will clarify some things. In a prospective study, let's say that I'm an investigator, and in 2008, I am interested in studying the impact of some exposure on the incidence of disease. Then potentially I could gather my population, and in 2018, I'm going to be classifying people based on who was exposed and who was not exposed. Then maybe 10 years later, because it takes a bit of time for the disease to actually develop in these people, I'm going to go back to these individuals and classify them based on whether or not they have the disease. So yeah, the prospective cohort study, I think, is the one that we intuitively think of when we think of a cohort study. That's one option. However, the problem with this option is that I need to basically wait 20 years for results, and maybe, I don't know, the grant that you have isn't going to pull you through for 20 years, or maybe you're just it's really important to understand the impact of the exposure on the disease right now. There's an urgency to it. So the prospective cohort study is not going to work well in that situation. In that situation, we might instead want to conduct a retrospective cohort study, where essentially you're going to be relying quite a bit on historical information, clinical records from the past, and so forth, in order to, if you're an investigator in 2008, you're going to define your study population based on information you have in 1988. Then you're going to classify them based on their exposure status and conduct all of your analyses, but you're basically looking back in time to gather your information. So I think just by thinking about them like this actually allows us to emphasize some potential problems with both. Just just summarizing, I think, the 2 biggest issues. The prospective cohort study is going to take a lot of time and a lot of resources. The retrospective cohort study, you're going to be relying a lot on past information, and that might not always be accurate or valid. So that can introduce biases in its own. And then finally, we have this other image to help us understand. A prospective cohort study is also called a concurrent cohort study. And so if we look at this arrow where it says now, this image helps us understand the difference between the prospective, the retrospective, and the ambidirectional. So I didn't talk too much about the ambidirectional. What's going on with the ambidirectional is that in the present, you might use a retrospective cohort study to go back and determine who was exposed and in who some sort of short-term outcome developed. But in an ambidirectional study, you might then want to follow the participants from this retrospective cohort study, which is the purple arrow in that third section. You might want to follow them to see with the green arrow who develops a long-term outcome of this potential exposure. So an ambidirectional study essentially is a combination of the prospective and the retrospective cohort study. So I kind of mentioned some of these, but the timing is going to matter. And when you are deciding whether or not you want to conduct a prospective, a retrospective, or an ambidirectional cohort study, there are some considerations. With a prospective cohort study, it's going to work really, really well if the outcome develops pretty quickly after having been exposed, because then you can gather your information very, very quickly. Additionally, I didn't list it here, but it's going to work well when you want to infer temporality between things like A caused B. That's something that in a retrospective cohort study is not going to work so well, because since you're relying on past information, it's going to be hard to determine whether in fact the exposure caused the outcome. A retrospective cohort study is going to work well when the outcome has a long induction or latent period, and when you just don't have enough grant money or resources to fund like some sort of 20-year prospective cohort study. And then as I mentioned, the ambidirectional cohort study will be ideal if you're interested in studying both short-term and long-term outcomes. So there's many different types of cohorts, but here I've just included the definition for 2 of these. Some cohorts can be considered fixed and others are considered to be more open or dynamic. So a fixed cohort is one where new members are not added after the follow-up period begins, but it is possible that you lose members after a certain amount of time. And a fixed cohort can also be defined when some sort of exposure that can never happen again or is likely to never happen again occurs. So we'll go through some examples of that. An open or dynamic cohort has a membership that is much more dynamic. It changes over time and people can come and go. And so we're going to discuss some examples of that too. So this example here is of a fixed cohort. The World Trade Center cohorts correspond to first responders, persons involved in cleanup after 9/11, persons that were present in Manhattan on that date. And the reason why this is a fixed cohort is because the incident of 9/11 already occurred, and we can't go back and people can't be added to the group of the individuals that were present in Manhattan on that date. So once the event has taken place, there's no introductions that can be made to this cohort. There's also many, many studies that have been conducted with fixed cohorts. So one example that I just pulled off the internet is this 1958 National Development Study, where individuals that were born within a week of 1958 in England, Scotland, and Wales were followed pretty much for most of their lives, I think. And this is a fixed cohort because once that week of 1958 that they were focusing on has passed, nobody can be added to this cohort. And what's cool about the study is that they've actually shown really, really interesting things about these people. One thing is how economic inequalities can move around generations, and how some mental health problems actually begin from childhood and can affect you later on in life. Some examples of open cohorts would be things like being a resident of Rhode Island, because some people might come and go, or the cancer registries, some people get on there to my understanding, but then can be removed and people are constantly being added. So it's much more dynamic than a fixed cohort. So going back to our original discussion about the general premise behind cohort studies, the way in which we conduct them is that, as I mentioned, it's very, very important that your population corresponds to individuals that are at risk of developing the outcome. You don't want to classify individuals based on exposure status and then follow them if some of these individuals already have the outcome, because that's not going to be very interesting. And it's not going to allow you to establish the temporality of, oh, the exposure caused the outcome. The second step in a cohort study is going to be to define the exposure of interest and then classify these individuals based on their exposure status, which is step 3. And then if it is a prospective cohort study, you're going to be following them over time to decide who develops the disease and who does not. So who falls into those different categories that we described in our 2x2 tables. And then finally, step 5, which I've been mentioning a little bit, is that we're going to be comparing the incidence of the outcome among the exposed to the incidence of the outcome among those who were not exposed. And that's going to be done by a measure of association through data analyses. So we're going back to our 2x2 table. In a cohort study, what a 2x2 table allows us to calculate are the incidence rates of disease. So the incidence rate of disease among the exposed is going to correspond to A divided by A plus B. Because when we're saying among the exposed, that means that we're considering everyone who was exposed, which is A plus B. And then we want the incidence rate of disease. So we're dividing this A plus B by the number of exposed people who have the disease. So that's number A. Then the incidence rate of disease among those who were not exposed, we're focusing on the group that was not exposed to the exposure of interest. So that's individuals C plus D. And then we want the incidence rate of disease. So that's going to involve dividing C by C plus D. And so a lot of the times when people are conducting cohort studies, there's many measures of association that can be reported. For the purpose of this talk, I'm going to be talking about the relative risk, but yeah, just keep in mind that there are, I just listed 3 of them, but there's a lot of different ones. And if you see specific studies with cohort studies, it might be that the authors chose to report the relative risk, the absolute risk, the odds ratio, the attributable risk, and so forth. But we're just going to focus on the relative risk. So the relative risk is a comparison of the incidence rate of subjects that were exposed to the incidence rate of subjects that were not exposed. So as I mentioned, the incidence rate of subjects that were exposed was A divided by A plus B, and the incidence rate of subjects that were not exposed is C divided by C plus D. So what the relative risk is doing is that it's dividing the first value by the second value and allowing us to compare how these incidence rates compare for these 2 populations. So let's kind of like untangle that formula a little bit. If A divided by A plus B is the incidence rate of subjects that were exposed, and C divided by C plus D is the incidence rate of subjects that were not exposed, then if the relative risk, so that whole thing, is equal to 1, then that means that the first value, A divided by A plus B, is the same as the second value, C divided by C plus D. So if those values are the same, then that means that the relative risk is equal to 1, and the incidence rate of subjects that were exposed is the same as the incidence rate of subjects that were not exposed. So that's why the interpretation of a relative risk of 1 is that there's a lack of association between the exposure and the disease. On the other hand, let's say that the relative risk is less than 1. So if the relative risk is less than 1, then that means that the numerator, which is the incidence rate of subjects that were exposed, so A divided by A plus B, is smaller than the denominator. So it's smaller than that C divided by C plus D. What that's saying is that the incidence rate of subjects that were exposed is smaller than the incident rate of subjects that were not exposed. And if that's the case, then it's very, very likely that the exposure has some sort of protective effect on the outcome. So being exposed leads less to the outcome or disease. And then finally, a relative risk greater than 1 means that individuals that are exposed are at greater risk than individuals who are not. So mathematically, what that means is that the first term, A divided by A plus B, is larger than the second term, C divided by C plus D. So here's an example of a 2x2 table, and it's actually been filled in. And I want to just take like 1 or 2 minutes. And I'd like for everybody to compute the relative risk for this 2x2 table. And then maybe also just think about how you'd interpret the relative risk in this case. And I will say the interpretation, I'll discuss it, but the interpretation is very much related to the ordering in which this happens. So the exposure comes before the disease. So yeah, let's just take like 1 or 2 minutes as a break. Okay, so if I did my math correctly, and hopefully everybody got that the relative risk is 0.25. So what that means, the interpretation of that relative risk is that those who were exposed were 0.25 times less likely to develop the disease than those who were not exposed. So in this case, the relative risk is less than 1, which if we go back to the previous slide with our interpretations, this indicates that the exposure has some sort of protective effect on the disease or outcome. So cohort studies are definitely not perfect. There's going to be some issues when you're conducting a cohort study that comes up. Here I hope to just very quickly discuss some of the biases that may come up in a cohort study and just things to be aware of. So when Jess gave her talk, she defined bias as any systematic error in the design, conduct, or analysis of a study that results in a mistaken estimate of an exposure's effect on the risk of disease. So essentially, bias is a mistake that's going to impact whatever you estimated the association between the exposure and the outcome being. So 2 potential sources of bias are selection bias and information bias. Selection bias occurs when there's been a mistake being made in how you've selected the participants for your cohort study, and information bias is going to pertain to mistakes being made with the data collection. Finally, there's a third issue, which is confounding, which I'll also briefly talk about, because confounding is a it's a problem that comes up very frequently in observational studies like a cohort study. So some sources of selection bias, which basically means that the participants that you've selected, there's some issues with that, are membership bias, non-response bias, and loss to follow-up bias. So with membership bias, what ends up happening is that it becomes a problem when your external comparison population, it ends up happening that the exposed and unexposed people are fundamentally different. So when we think about membership bias, a lot of the times, the example that comes to mind is the healthy worker effect, because it helps illustrate this issue. If you are conducting a study on, I don't know, the relationship between smoking and not smoking, for example, and your study population are a group of workers, and you end up getting, let's say, relative risk for your study. The problem is that it's very, very possible that whatever you've estimated isn't going to directly generalize to the overall population, because workers tend to, on average, be healthier than your average person. So this could be a problem because it might lead to overestimates or underestimates of the relative risk. Similarly, if you pick, for example, again with this healthy worker example, if you are studying the impact of some sort of exposure in the workplace versus an exposure, and you're comparing it to groups of people that were not exposed that, I don't know, just stay at home or something, again, it's going to lead to this healthy worker effect and hence membership bias, because workers are on average going to be healthier than individuals who do not work. And so when you're estimating the relative risk for that study, it's also going to be impacted by the fact that everybody who, say, was exposed is also a healthy worker. Another source of selection bias that can come up in a cohort study is non-response and loss to follow-up. And both of these are pretty similar. With the non-response, it's very, very possible that the individuals who end up volunteering to do your cohort study are actually different than the people who do not volunteer. And so that's also going to lead to some concerns regarding generalizability and how much your estimate can really apply to the population that you're actually interested in. And then another issue, loss to follow-up. Yeah, even though you might get volunteers who represent your population well, it's very, very possible that you might lose some people along the cohort study, and that the people that you lose are actually going to impact your measure of association that you're trying to calculate. So, for example, a lot of the times with cohort studies, let's say that you're looking at people who were exposed to some sort of exercise intervention versus people who decided not to exercise. If for some reason the intervention isn't having the effect on the person that they wish it did, like they're not losing the weight they want to be losing, then they might drop out of the study. And if the people who are dropping out are individuals who, let's say, aren't motivated, then when you calculate your relative risk, you're not taking into account that a lot of the individuals in the exposed group that remain are the motivated people, because the people who aren't motivated to do the exercise class just dropped out. So loss to follow-up, especially in a prospective cohort study where you're following people over 20 years or maybe even more, is definitely a big, big problem. Loss to follow-up can be seen in the form of not being able to locate the person, and also just the individual withdrawing due to their own personal reasons. At the start of a cohort study, you can definitely minimize this loss to follow-up by making sure that you collect personal information and that you're regularly contacting these individuals. I think two other points that I included that are important is that it's important to make the individual want to participate in this, because if you're making it so that the study is so complicated and involves so much of their time that they don't want to participate, then they're likely going to withdraw or just be lost to follow-up. And that's very much related to minimizing participant burden. You want to make sure that the expectations of your study are realistic, and that you're not complicating everyone's life with your study. And we kind of alluded to this in the randomized controlled trial seminar, but if participants are actually lost to follow-up, then your data analyses methods are likely going to have to account for that. You're going to have some missing data, and you're going to have to use missing data techniques or other sort of statistical analyses to be able to account for the fact that these participants are lost to follow-up. Because as I mentioned, a lot of the times when individuals decide to withdraw or just remove themselves from the study, there's reasons behind these, and there's certain characteristics in individuals that make them more prone to be lost to follow-up. So it's important to account for these when you're conducting these studies. A lot of the times, I was actually reading one of the cohort studies for this talk, and a lot of the times if you read the methods section very, very carefully, they actually say things like, oh, I don't know, our study had 80% retention rates, or that means 20% of individuals were lost to follow-up, and notice though that the baseline characteristics of those lost to follow-up are very similar to those who remained in the study. And what the author's trying to do there is they're trying to kind of address this issue, which is they're trying to say, look, we did lose 20% of the individuals, but these individuals were pretty similar to the ones that did stay in the study, so we hope you believe whatever results we came up with. Another type of bias is information bias, and essentially this comes up when the way in which information is being collected can lead to some potential misclassifications. So for example, if the one type of bias, information bias specifically, is interviewer bias, if the interviewer knows that someone's been exposed, then they might be more likely to assign them to some specific outcome because, I don't know, they have like some preconceived thought that like the exposure leads to the outcome or something like that. Additionally, bias can also be introduced from the respondents. So if you know that you've been exposed or not exposed, you might answer questions differently than someone who does not have the same exposure status as you, and that's going to impact results as well. Some potential solutions to these types of biases is to blind the individuals collecting this information from exposure status, and to also make sure that when we're measuring the disease, we use objective measures as much as possible. So not just relying on historical information, also using maybe biomarkers or other types of information. And finally, just making sure that however you're assessing the outcome should be standardized, so it shouldn't differ depending on whether you're exposed or not exposed. So the third type of potential issue with a cohort study is that of confounding. And confounding occurs when whatever measure of association you're trying to estimate is impacted because the primary exposure of interest is actually mixed up with some other factor that's also associated with the outcome or disease. So in this example, we're trying to estimate the relationship between physical inactivity and heart disease, but it's necessary to account for this third variable, which is age, in order to properly estimate that relationship. So this is an example where age is a confounder of the relationship between physical inactivity and heart disease. So as I mentioned, confounding is a problem that does come up in most observational studies, and it really traces back to that fundamental difference between observational and experimental studies that I mentioned, which is that individuals are self-selecting their exposure status when it comes to observational studies. So there's many different reasons that can explain the self-selection, and it's necessary to address them. When researchers are trying to address confounding, you can either address it at the design phase or you can address it in the analysis phase. What I mean by the design phase is maybe prior to actually conducting your study, you try to think of ways to reduce confounding. This can be done by restriction and matching. So for example, actually this example is with case controls, but it's okay. With matching, what you would do is that for every person who is exposed, or for every person that you're considering, you find someone else in your study population that is very similar to them when it comes to baseline information. And then you include both of those people in your study, because since they have similar backgrounds, the amount of confounding error that might occur is limited. So matching can actually, it's a very interesting statistical tool, because you can actually do matching in the analysis phase as well. But yeah, it can also be done in the design phase. If you're like, okay, it comes up more often in case control studies, but yeah, I'm gonna recruit a case, then you might wanna match them with a control who's very similar to them. So somebody who has the same age, who's the same gender, who has the same socioeconomic status, and so forth. And that way you're reducing the potential other variables that could impact whatever measure of association you want to estimate. Confounding can also be addressed in the analysis phase by stratifying all of your measures of association. So for example, those 2x2 tables, you could actually create multiple tables based on different variables or so forth. And therefore you'd have multiple relative risks depending on whatever variable you're stratifying by. Another way to address it is using multivariable models that try to kind of control for these confounders. And then finally using propensity scores or inverse probability weighting. So as I've kind of been mentioning there's a lot of advantages to using a cohort study because it allows us to follow individuals over time and really help establish why did people develop the disease, or who is the disease more likely to develop in those who were exposed or not exposed. Additionally, one very, very nice thing about a cohort study is since you're classifying individuals based on their exposure status, you can also look at multiple health outcomes. And so if you are interested in one particular risk factor and how it impacts other health outcomes, this could be a very, very valuable study design. And then finally, it does work very, very well for looking at associations with rare exposures, because since you're selecting individuals based on their exposure status, you can basically recruit a group of individuals who has this rare exposure and follow them over time rather than just waiting to see who has the exposure that's rare. We've discussed the disadvantages. They can take a really, really long time to conduct. They are more expensive than the case control studies, which we'll discuss, and the cross-sectional ones, which just discussed in the previous seminar. A lot of the times, loss to follow-up is a huge issue with these, so it's just important to keep these in mind. I have a couple examples of cohort studies, but I think in the interest of time, I'm only going to discuss one of them. The British Doctors Cohort Study was one that was conducted between 1951 and 2001. And what they did is that they recruited a bunch of doctors. I think it was 34,439 doctors. And the reason why they were focusing specifically on doctors and following doctors over this 50-year time period is because they actually thought doctors would do a good job at recording whatever they were experiencing. And also they thought it would be easy to establish when a doctor has passed away and when it hasn't. So that's why their cohort was limited to doctors. But they followed them for this 50-year period, and they actually published a lot of different studies with this British doctors cohort. This is just one of them that was looking at the impact of smoking on mortality. So the exposure was smoking and the outcome was mortality. And this paper is really, really interesting because it basically looks at when all these different men started smoking and their risk of dying relative to when they started smoking. So, and then it also looked at like when they stopped smoking and how that impacted their mortality, because some people stopped smoking at a relatively young age while others never stopped smoking. So it was very, very interesting. I think that the results are definitely very, very useful because since these individuals were followed for such a long amount of time, and it was a pretty large group to begin with, it allows us to definitely establish temporal associations with these issues. And then there was another cohort study that I wanted to discuss, but I don't think I will. This is called just the Nurses' Health Cohort, and there was a study related to this Nurses' Health Cohort that was conducted that basically was looking at the association between optimism. So the exposure here was those who were optimistic, and the outcome here was mortality. So it was just looking at the association between those things, specifically for the nurses cohort. So just to review cohort studies, we're starting with a group that was exposed and a group that was not exposed, and we're following them over time, and we're seeing how the incidence of the outcome compares in the exposed group to the unexposed group. And now I'll start talking about case control studies. Are there any questions right now, or can I just, oh yeah, go for it. Yeah, confounding, I'll go back to that slide. Oh, sorry. The question is if I can go over the definition of confounding one more time. So confounding, I think this is actually a really good definition of it, but the issue with confounding is it's basically a variable that's impacting whatever you've calculated the association between your exposure and outcome to be. So it's some third variable that comes in and is kind of messing up that association that you've calculated. In this case, that third variable is age, because a confounder, yeah, this is like a little bit more epidemiological, but a confounder needs to be related both to the exposure and to the outcome. And since age is related to both physical inactivity and to the outcome, which is heart disease, here it would be classified as a confounder. But yeah, we can think of a lot of different things that could be potential confounders. So I don't know, one that comes to mind is like in weight loss studies, a lot of the times a confounder, yeah, weight loss studies looking at, I don't know, heart, maybe like lung diseases. A lot of the times a confounder is whether or not the individual smokes, because smoking is related to an individual's weight, and then it's also related to lung disease. So you'd have to adjust for that prior to estimating that effect. Okay, so case control studies. With case control studies, we're kind of reversing a cohort study a little bit, because we're starting with a group of cases and we're starting with a group of controls. So cases, and I'm going to use cases and disease interchangeably, but cases are individuals who have the disease and controls are individuals who don't have the disease. And with the case control study is that you have these cases, you have these controls, and you're looking back to see who was actually exposed. So the reasons why you might want to conduct a case control study and not rely on a cohort study is, there's many reasons, but one of these that's I think very, very important is if you're studying a rare disease. Because if you're studying a rare disease, as I was mentioning in the cohort studies section, if you're going to just look at your groups of individuals that were exposed and not exposed and follow them to see who develops this rare disease, it's very, very likely that you're going to end up not learning much about the rare disease, because if the rare disease, let's say there's a 1% chance of it taking place, even if you have 100 participants, only one of those people in your cohort study is actually going to develop the disease. On the other hand, with a case control study, you can say, okay, I'm interested in studying this rare disease, so I'm going to start with 50 people that have the disease and 50 people who don't have the disease, and I'm going to learn about this disease through these 100 combined people. So a case control study works really, really well in this setting. Additionally, it's going to work well in settings where the cohort study does not. So in a situation where it takes a very, very long time for the disease to actually develop, because you're not going to want to wait so long for your results. And so you might be more inclined to just rely on starting with the cases and controls. Finally, I think another important one is if you, which I didn't mention here actually, is if you want to study the impact of multiple exposures. So if you want to learn more about some sort of disease, and you might want to conduct a case control study, because it's going to allow you to look at these cases and look at these controls and determine what type of exposures might have led to the cases and controls. So a case control study and a cohort study, I think the more you kind of learn about them, it's almost like they're opposites of each other and they work well in different situations. But they also can go hand in hand, and they often do. So I've kind of mentioned all of this, but the general idea behind a case control study is that you're going to be sampling cases from some sort of source population, and then you're going to be sampling your controls from the same population that produced the cases. And then once you have both of these, you're going to be looking back and determining who was exposed. So who in the cases were exposed and who in the controls were exposed. And then you're going to be comparing some sort of measure of association. So here it's going to be the odds of exposure. So again, this looks a lot like our cohort studies diagrams that we looked at. For case control studies, you're going to have one group that has the disease, another group that does not have the disease. But again, since you're looking at some sort of binary exposure, you're going to end up with 4 groups. And these 4 groups are very similar to the 4 groups we discussed with the cohort studies, but I do think it's important to keep in mind that here you're classifying individuals with the disease first and then looking at the exposure status. So immediately that should lead us to realize that we can't necessarily establish temporality as well as we did with cohort studies. We can't really say, oh, the exposure led to the disease, because we first classified on the disease. So we can't say that the exposure led to the disease when we didn't actually see this happening. With a cohort study, you can do that a little bit better because you actually followed the people to see that. So even though I said I feel like they're a little bit reversed, it can also just be thought of as a more efficient cohort study. We end up estimating the size within the controls and within the cases of the individuals that were exposed within these two groups. So one thing that really matters with the case control studies is how you decide to sample your cases and how you decide to sample your controls. And I'm not going to go into too much details about this, but it is very, very important to keep some things in mind. So when you're sampling your controls, your results can be very, very sensitive to how you decide to sample these controls. So a lot of the times when case control studies are reporting results, they actually report the results of multiple control groups because that's the understanding that different control groups can lead to different measures of association. And that's something that I'll actually explore in an example. But whether whatever way you decide to sample the cases and controls, it's very important that you do in fact establish prior to beginning your study that they are in fact cases and controls. So conducting some sort of test or verification of the fact that they're cases and controls should be conducted prior to beginning all this data collection. So as I mentioned, a case control study is very similar to a cohort study, but the ordering matters. With case controls, we're first selecting our cases and controls, and then we're measuring who was exposed and who was not exposed. So we do end up with a very, very similar 2x2 table, but the interpretation of these values changes a little bit because we weren't following the individuals the whole time. So in a case control study, we can summarize our findings again in this 2x2 table. And what we're going to be doing is that we're going to be comparing the proportion of cases that were exposed to the proportion of controls that were exposed. So since the total number of cases is A plus C, the proportion of cases that were exposed is A divided by A plus C, and the proportion of controls that were exposed is B divided by B plus D. And in a case control study, again, I only mentioned 2 of these, but I do want to emphasize that the measures of association or the measures of risk that you report are a little bit more limited than in a cohort study because you can't infer this risk or temporality aspect of it because you first classified based on disease status. And so because of this, we can't really talk about relative risk, but we can talk about the odds ratio, which is a very, very good estimate of the relative risk many, many times. So I'm going to discuss data analyses in case control studies using the odds ratio. The odds ratio is the ratio of the odds that the cases were exposed to the odds that the control were exposed. So the first value, the A divided by A plus C divided by C divided by A plus C, is the odds that the cases were exposed. And the second value, the B divided by B plus D divided by D divided by B plus D, is the odds that the controls were exposed. So if we go through and we can cancel those A plus C's, and then we can also cancel the B plus D's, we're going to end up with A divided by C divided by B divided by D, which just leads to AD divided by BC. And so I know I said a lot of letters, but the odds ratio ends up being just also known as the cross product ratio because it's AD divided by BC, which if you go back to the 2x2 table, that's the diagonal, it's the ratio of the diagonals of the 2x2 table. So the odds ratio nicely has like very similar interpretations to the relative risk. An odds ratio of 1 is going to indicate that the odds of exposure among the cases, so the first term, the A divided by A plus C divided by C divided by A plus C, that first term is the same as the odds of exposure among the controls, the second term. And if the odds ratio is equal to 1, so if these odds are in fact equal to each other, then you can say that the exposure is not associated with the disease. On the other hand, if your odds ratio is, let's say, greater than 1, then that means that the first value, so the odds of exposure among the cases, is going to be greater than the odds of exposure among the controls. And in this case, the exposure is a risk factor because the odds of being exposed among cases is greater than the odds of being exposed among controls. So I wanted to again look at an example of calculating the odds ratio for this 2x2 table. Since I'm running a little bit slower than I thought, I'll just tell you what the odds ratio is. But essentially we can find the odds ratio again by just taking the diagonal products and then dividing AD divided by BC. So the odds ratio for this 2x2 table, which is just looking at the exposure status of cases and controls, ends up being 32.7. So what this means in the context of this example is that the odds of exposure to raspberries was 32.7 times higher in cases than in controls. So this is showing that having consumed the raspberries is likely a risk factor for whatever outcome the cases have. So in case control studies, there are also sources of bias, and a lot of the times the bias is coming from the way in which you select your cases and your controls. One particular problem really comes to do, like the cases are usually selected in a pretty good way. Like that's not usually the biggest source of problem, but the biggest source of problem is usually how you decide to select your controls. It really makes a difference whether or not your controls are representative of the population that produced the cases. So I'm going to show you this example to kind of emphasize this. So if we read through this very quickly, essentially this is a hospital-based case control study that is looking at how alcohol consumption is associated with the development of this liver outcome. And originally they select controls to come from hospitalized trauma patients. So their cases are individuals who have this liver disease, and then their controls are individuals from the trauma ward. So that's the first two columns in this table. When they pick these controls and they do their odds ratio calculations in the same way that I just showed you by taking 80 times 60 divided by 40 times 20, they end up finding that the odds ratio is 6. However, this odds ratio is very highly impacted by picking a different set of controls, which is individuals who were not in the non-trauma ward. So if we do the odds ratio with this different set of controls, so 80 times 90 divided by 20 times 10, you end up getting that the odds ratio is 36. So why do we get such different values? Like that's a little bit concerning because one is saying, like even though they're both saying that the exposure, so having heavy alcohol use is definitely more prevalent among the cases, those are very, very drastically different values. So the problem here is that the way in, if you use the controls in column A, so controls A from the trauma ward, you're not sampling those individuals from the same population that the cases came from. So the cases, which are individuals that are in the hospital with this liver disease, are individuals that were sampled from the general population. And if you're using controls from the trauma ward, individuals in the trauma ward are likely to be in the trauma ward. I mean, not always, but they might be in the trauma ward because they've consumed a lot of alcohol. And so since the way in which you've selected your controls is actually related to your exposure, that's impacts odds from the same controls that came from the same population as the cases, which are controls B from the non-trauma ward, you find that the odds ratio is much higher. And we actually would believe the second odds ratio of 36 more because the controls were sampled from the same population that the cases came from. So again, I think a lot of researchers really do know that the way in which you sample the controls really, really matters for the study design. And so they do put a lot of emphasis on this. I think both of the case control studies that I included as case studies included multiple sets of controls precisely for this reason, because if you don't sample your controls properly, you might have different measures of association being estimated. So with case control studies, aside from having selection bias, which is what I previously discussed, information bias is also a concern. You might have issues with people actually remembering their exposure status, because you're selecting individuals based on whether or not they have the outcome or disease. So it's going to be hard for them potentially to remember whether or not they were actually exposed, and that might lead to misclassifications. Additionally, with individuals that are interviewing these cases and controls, it's very possible that the interviewers might probe the controls more carefully than the cases, or vice versa, and that can also lead to misclassifications. So one thing that definitely helps is very similar to the cohort studies, to just make sure that you're using standardized techniques for verifying the outcome, and also maybe potentially blinding the interviewers to the case and control status of the individuals in the study. So some advantages of case control studies is that it can be very, very cost effective to conduct relative to something like a cohort study, because you basically are just, you have a bunch of cases and a bunch of controls, and you're determining who was exposed and who was not exposed. There's not really a need to follow them over time and a really long waiting period. So that might work very, very well for certain study questions. Additionally, as I mentioned, it can be very, very efficient when you're trying to look at multiple exposures. So if you have some sort of rare disease and you're trying to understand why that rare disease might develop, then you might want to conduct a case control study, because having this very, very large sample of cases might allow you to understand which factors are potential risk factors for this rare disease. Again, as I've mentioned, some of the disadvantages of case control studies are that it can be prone to lots of different types of biases. We do have some issues that come up when we're selecting our control subjects, and sometimes it is hard to establish temporality, which is something that a lot of the times we want to be able to say, oh, exposure X causes outcome Y, and that's something that's very challenging to do with a case control study. So again, I had two case control studies, case studies, but I'll just focus on one of these. So this is a huge case control study. It's called InterHeart. And essentially what they did is that they were looking at acute myocardial infarction in 52 countries. And they had a total sample of 15,152 cases and 14,820 controls. And for this outcome, they wanted to look at various risk factors. So they wanted to see whether, I don't know, smoking, history of hypertension, waist to hip ratio, physical activity, and so forth, the impact of those factors on having acute myocardial infarction. So what they did was they had this large group of cases and controls, and they basically estimated a bunch of different odds ratios for all these different risk factors. And they end up finding a bunch of different results. But as you can see, they are reporting these odds ratios, which is what we've been discussing for case control studies. And their final findings are that many issues do help account for the risk of acute myocardial infarction, like abnormal lipids, smoking, diabetes, and so forth. And their interpretation of this is that by knowing these issues, we can hopefully prevent future cases. And yeah, in the interest of time, I don't think I'm going to go through the bulimia case study. But yeah, just to review, unlike cohort studies, we're starting with whether or not the individual has the outcome, and then we're determining their exposure status after having really solidified whether or not they're a case or a control. And then this table, I know it's a little bit hard to see. I just thought that it really helps clarify some of the issues with cohort and case control studies, and it really provides a comparison between all of these. For those of you who are interested in getting access to this table, I can send the table to whoever's interested. But yeah, I just thought it provided a really, really good summary of when you'd want to use it, what types of risk measures we can estimate with these. I think the next page provides like which of these are expensive, potential problems, potential biases, and so forth. So I just thought this was really interesting. But yeah, just to conclude, a lot of the times when you're conducting these studies, what we first see when you're trying to determine the association between some exposure and the outcome is that we see a lot of case control studies being conducted first. So a lot of the times case control studies are conducted, they find some sort of association, and then individuals decide to put money and resources into further investigating these associations through a cohort study. So yeah, a lot of the time I think you learn these things and you're like, okay, but what should I do in my specific situation? And I think it really does depend. But yeah, most of the time the results of a case control study can help motivate the development of a cohort study. So thank you so much for listening. I'm sorry I went a little bit over, but are there any questions or comments? Yes.
Okay. Sometimes, and I'm like a molecular biologist who would look at an epidemiology paper and then try to interpret it, I'll see a relative risk of say 1.25.
Mm-hmm.
And I know that's small relative to like 6 or 12, like, for other smoking, but is a relative risk of 1.25 considered significant or big? I mean, not statistically significant, but just when you see that, is that something that?
Yeah, no, that's a good question. I think the first part would be, and it's funny because I wanted to mention that actually and I did it, but I think it's, sorry. Oh, I'm sorry, I keep on forgetting that. The question is whether or not a relative risk of 1.25 is actually statistically significant or just large relative, because yeah, we know a relative risk of like 30 is large, but is 1.25 large? That's the question. So yeah, I think that's a great question. I think a lot of the time when we report these things, it's very, very important to report the 95% confidence interval, because if you as the investigator, you're just interested in knowing whether the exposure does have whether or not it is a risk factor for the outcome, then all you're going to be caring about is whether or not that odds ratio or that relative risk is greater than 1. So if the 95% confidence interval is, the entire confidence interval is above 1, then yeah, that would allow you to potentially conclude that, or you have evidence to conclude that. Yeah, I think a lot of the times that you're right, that 1.25 really means nothing when you don't attach those measures of uncertainty to them, because if it's 1.25, but your sample size is really, really small, so I don't know, the 95% confidence interval is between 0.5 and 10, then yeah, that 1.25 means nothing. While something like having an odds ratio of 36, then you'd be like, okay, my confidence interval is likely above 1, so it definitely has an impact. The interpretation of that exact 1.25, assuming that it is statistically significant, I think again that varies depending on what you're studying. If the exposure being a risk factor for the disease is really like a life or death sort of situation, that 1.25 might mean a lot to you as a clinician. But if it's something where it's not all that, it doesn't really lead to this horrible outcome, then 1.25 might not be worth investing like hundreds of thousands of dollars into or anything. But yeah, I think attaching that uncertainty is really, really important. I think a lot of times people are really focused on the point estimates of the values, but the uncertainty matters just as much, I would say. It's a good question. Are there any questions online or no? Okay, cool. Oh.
I have one more question. I was just saying, is there a formal way to weight an exposure? So if you're looking at a cohort group, or like a statistical method of weighting an exposure, so like they smoked a cigarette, but they smoked 40 cigarettes. you know, it's rather than a black and white.
Yeah, yeah, yeah.
Putting it at like a weighted confounder. So if you're just looking for, they use this medicine, you're looking for lung cancer, they were a smoker. So it's like the confounder could be a smoker. So it's like, can you weight a confounder? Or can you weight the exposure?
Yeah.
Just making more rows in our
Mhm. Exactly. You could, that's a great point. You could definitely categorize all these things differently. So yeah, your 2x2 table could become, I don't know, if you have 5 different categories, it could become a 5x2 table. And then your analyses would just have to be adapted to that. So I know in one of these studies, maybe I can find that, but yeah, maybe. Yeah, like here, I'm not sure. Oh yeah, smoking, actually, just what you were talking about. So here, when it's reporting the population attributable risk, it's actually saying for current and former versus never. So yeah, there are multiple categories and they're trying to summarize this information differently. But I'm sure that in their analyses, when they were computing all these things, they were stratifying by all these different categories. Because you're right, sometimes the exposure isn't going to be binary and you're going to want to capture, okay, what's the difference between someone who smokes 1 cigarette versus someone who smokes 10 or whatever.
I have Carolina from URI, and she just wanted to say thank you, and she found it extremely helpful.
Oh, thank you. Thank you, Carolina. Thank you so much. I'll hit stop share.
Yeah, it's stop broadcast.
Okay, cool. I think I've hit stop share.
That's fine.
Leave
Meeting.